So welcome again to the next talk. We have Ioan Mărcuț from Radboud Universiteit Nijmegen, and he will talk about the rigidity of PDEs with symmetries.
I hope this stays there.
If not, it will fall.
That's what I.
So, thank you very much for inviting me here, and I'm very happy to be at the first in-person workshop in a very long time. So, and I see that my talk was exactly after Florian's, and it's very much connected to Florian's talk. So I hope people were very listen to that, and I can kind of a little bit build on that. So this work that I'm talking about, I also talked many times before, and maybe more than half of the people here heard versions of this talk. I'm not completely convinced, and that's the case. And it's a work which I did with Roy Wong, who was a PhD student in Utrecht, and now he's working at the bank for some time. And we didn't really finish the paper yet. I still have to do that now, but I think it only needs a nice introduction, and that would be it. So what we try to do is make some sort of analytic tool which can be used to prove results like the one Florian talked about. So normal form results for various geometric structures, and by using the Nash-Moser technique, but putting them in a setting which is kind of simple to apply in applications. So you just use that setting, and then you apply it, and then you obtain, well, you still have to prove something, but you obtain a normal form result. Now, the way we stated it does not work, of course, in all cases. It doesn't even work in what Florian talked about before, but I'll tell you a little bit later what the differences are. So, right, and then the setting in which we're putting things is like, you have a solution of a PDE. This PDE has a group of symmetries, and you want to show that that solution is like it's, well, if you act with the symmetries in that solution, you obtain something open in the space of solutions, which means that every nearby solution is conjugated to this one. This is somehow the idea of the theorem, and that's what we mean by rigidity. I'll make all these things more precise later on. And by proving such a property, this can be used in many cases to prove normal form theorems. By basically proving that the local model, the structure that you want other structure to be isomorphic with, is rigid. And then you bring other structure very, very close to it by deforming that. Okay, but I will. So this was the introduction. Now I'll go kind of slow in and talk about first about, well, stating the results. So I will even go slowly and talk a little bit about jet bundles first. So let's take E over M, a vector bundle. And just to fix notations, I will denote by JK of E over M, the case jet bundle of E. Right, so this is a new vector bundle over M whose elements at a point, I will also write this here now, so take the fiber over at a point P are, well, you look at all the sections and you mod out by sections which vanish up to order K at P or K plus 1. So let me just write it like this. So these are sections of E over M modulo sections which vanish, and this you can realize as the vanishing ideal of P at the power k plus 1 times the space of all sections. And so this is a description of the kth jet bundle, and if you start with a vector bundle, what you obtain this is again a vector bundle. And so this can be used to, of course, to introduce norms on the section. So if, for example, so I will assume most of the time that this M is compact. And then if you just fix some norms on these vector bundles, as bundles, you obtain CK norms on the space of sections, right? So if, let's think of them like this, GK are norms on the kth bundle over M. Then you obtain CK norms on the space of sections. E is simply taken by the supremum of the kth jet of a section. So if sigma is a section of M over E, then it's kth jet of sigma. This will be a section of the kth jet bundle. And you define the norms of sigma. The norm of sigma k could be the supremum norm of all this jk sigma at the point P. So you take the supremum over M. And this is with respect to the okay, and then if you put all this together, if M is compact, you obtain a Fréchet space. So the space of all sections of E together with all these norms. Okay, this forms the space. This was mostly to introduce notation, and now how is it if I go any higher than this, then the people at home will not see anything. If I move this down and write on the blackboard, then maybe we can go this high. Okay, I have also this board. Right. And then, okay, so the way I would state this theorem will be in the setting of natural bundles. I think this is kind of a simple setting where the symmetries of the PDEs come from basically all the diffeomorphisms of the things. And then let me also introduce this natural bundles. This is a notion which is kind of used, also people in symplectic topology use it sometimes to state things. So let me also talk about this a bit. So natural bundles. So this is simply, and just for simplicity, I will only talk about vector bundles. So a natural bundle is simply it's a vector bundle, and then plus a lift of local diffeomorphisms of M. So with a lift of local diffeomorphisms. Right, so this means that whenever I have two open subsets of M, so let's say U and V are two open subsets, and I take a diffeomorphism between U and V5. This natural bundle comes with a natural lift, so a vector bundle automorphism between the restrictions E to V, and I'll call this phi with an atom.
The vector bundle with the connection, with that connection will do.
So that would lift vector fields. That would lift vector fields, also vector fields, but I don't think it works in general for the entire diffeomorphism. I think Poisson would know the answer to this. it does not work in general. Right, and then such that this satisfies usual axioms like compatibility, so compositions, which will preserve compositions, and unities and restrictions, so or identities. Restrictions. And then the standard examples of this are the natural bundle. So, tangent bundle, of course, when the lift is simply the differential of the local homomorphism. And then a lot of bundles which are built out of this form. So, differential forms or homomorphisms. And so on. In fact, there is even a classification of such bundles. So natural bundles, they are all bundles associated, if M is connected, they are all bundles associated to a jet bundle. So I don't want to talk more about that right now. Right. So I will state everything in terms of natural bundles, and then the PDEs I will look at will be also basically what one could call a natural PDE. So it is Is the microphone too close to my nose? Is this better? Yeah. Okay. But you can still hear it from the book. I'm not sure if the people in the recording will hear it. Try something in between. Okay, so these are natural bundles, and now I was saying that I will talk about natural PDE. So first of all, let's think just about what PDE is, and for that I will use nonlinear partial differential operators. Nonlinear partial differential operators. Such a thing is a map Q which goes from sections of one vector bundle M E to sections of the second vector bundle F, and it is of the form, so it factors through the jet bundle. Q of a section sigma is simply you take if the differential operator is of order k, it means that you take the kth jet of sigma and apply to it a smooth map Q, where this Q is a bundle map, the fiber bundle map from kth jet bundle of F. Right, like this, okay, covering the identity. Okay, so I will look at such maps. These are nonlinear PDOs, and I write here nonlinear to make the difference to linear ones, but they're not nonlinear.
So you mean none of F comma? The first line. F is a bundle.
Yes. It's sections of E.
Yeah. No.
Which are defined on them.
Yeah, sorry.
It's just a matter of no. I think I actually prefer sometimes the notation from algebraic geometry where they write something like this. E of M for sections.
So the bundle map is not the vector bundle.
No, yeah. It's non-linear. Yeah. So if it was, then it was exactly a linear partial differential operator. And then a PDE, I'm thinking about the PDE simply as being this equation, sigma, Q of sigma equals, let's say, 0. Okay, so this is the kind of PDEs I'm looking at. They are quite general, if you think about it. And then let's say that a natural PDE would be one which is between, so a natural PDE would be one where this E and F are natural, so E and F are natural. On this. And the map Q is equivariant. But that's something I didn't quite explain, right? So whenever, so natural and Q is equivariant. So Q of pulled back by a diffeomorphismal section should be the same as the pullback. No, this is this line I cannot cross. Should be 5 star. So this is natural over this phi. I think it's quite clear how to make sense of this at the level of sections, right? So if we go back here, if I have here a local section, let me think what would be the pullback. So if here is a local section sigma, then the pullback is the thing which makes the diagonal commutative, so sigma, vice versa sigma. And so it's basically you do phi, you do sigma, and you do phi happy minus 1. Okay? It is clear. So you have this action. And I'll call such a thing a natural partial differential equation, something like Q of sigma equals 0 in such a setting. And now let me give examples. So first of all, you could, I think one simple example would be, for example, you take closed differential forms. So if we take, let's say, E to be wedge P of T star M, F to be wedge P plus 1, T star M, and then Q to be simply the round differential, then the solutions are simply closed P forms. Something that I'm working more with, and Florian also talked about our Poisson structures. The Poisson structures are sections of the second exterior power of Tm, and then the Poisson equation. Well, it's you take a bivector field and send it to pi graphic pi. This is a Q is a differential operator, which is nonlinear. Right? In the first case, it wasn't linear, but this is nonlinear, it's quadratic. And this gives you a 3 vector field. Right? So pi bracket pi equals 0. These are Poisson structures. Maybe to include another example are complex structures, right? So a complex structure, you can think about it as an involutive, almost complex structure. An almost complex structure is first of all an endomorphism of the tangent bundle, right? J, which satisfies two equations. So J, here you could send it to J J squared plus the identity. You want it to be an almost complex structure, so it's 0 means that J squared is minus the identity. And the 9-house torsion of J, you want to be 0. I'm not going to write a formula for this, but this is the 9-house torsion. And this maps of these two parts, one is again an homomorphism of Pm, and the other one is the 9-house torsion. I think it's like wedge 2 of T star M tensor Pm. Okay, and then the solutions are complex structures. Is everything clear so far?
Is there a reason why you don't put the J squared equal to minus the identity already in the E?
There is, but it's a bit silly. The reason is just that I'm working with vector bundles, but I could work with fiber bundles, and then I could put it in there. And it's just to simplify later a couple of things. So I'm working with vector bundles. Okay, so now I will tell you what I mean by rigidity of such a solution. And as I said before, it simply means that the orbit of the solution is open in the space of all solutions. Right? So the setting is, well, should I write this again? So Q, let me write it like this: Q of sigma equals 0 is a natural and we take sigma 0 solution. So sigma 0, so Q of sigma 0 equals 0 is a solution, and then we call this solution rigid. So sigma 0 is rigid if there exists a neighborhood, called curly V, inside the space of all sections. So this is a neighborhood of sigma 0. So with respect to the Fourier topology, which means it's a CK neighborhood for some k, such that if you take any other solution in this V, the two are isomorphic, such that for any sigma in V with Q of sigma equals 0, it follows that there exists a diffeomorphism M, which relates them such that sigma 0 is phi star of sigma. Right, so in other words, it's exactly what I said before. The diffeomorphism of M times sigma 0 is open, or is a neighborhood. Actually, is a neighborhood of is a neighborhood of sigma 0 in Q times 0, right, in the solution space. Right, so the fact that the diffeomorphism group acts on solutions comes from the fact that this partial differential operator is equivalent, it's natural, and the PD is natural. Right, so this would be the definition of rigidity. Is this clear? Is this very long or I don't know? For people? Yep.
So should I be a local diplomat?
In this case, I'm writing something global. Writing something global. But the main point is exactly this, that so this would be, let's say, for M compact, but for M without boundary. And if M has boundary, I will change this definition. And that's actually the case which we are kind of interested in, because for this local normal form theorems, we have somehow a solution which is defined on, I don't know, around the point on a closed ball, and then you have to find a diffeomorphism between it and the normal form, but the diffeomorphism will be defined on something small. You actually have to shrink the radius on which things are defined. Right, so this definition is in the case where M, as before, is compact, but the boundary of M is N.
These neighborhoods, can one understand them also like the finite dimensional neighborhoods on N and the fibers of E?
Yeah, exactly here. Yeah, it would be a CK neighborhood. So all the things whose CK, so let's say it would be sigma minus sigma 0 index k is smaller than x. It would be something of this.
All right, I understand. But is there some intuitive understanding in finite dimensional terms on M and E?
On M and E,
and the image of the graph.
I don't know exactly how to answer that.
Well, the graphs of sigma 0 are open. So
okay, so maybe I don't know. First, I wanted to write over the definition where the boundary is non-empty, but maybe I'll write it again on the next word. So I have until when should I stop?
You should stop at 10 past 4.
10 past 4. Okay. I think it's better if I write also this. So when the boundary of M is non-empty, of course one could write. Sorry, one could write, of course, the same definition for rigidity, and that's a definition. But I think in most examples that's not what happens somehow. And I'll give you very soon one example. So this is why one should really change this. So I'll define the same. So think about it. It's exactly the setting. So we have a natural PDE and a solution of sigma 0 equals 0, but the only difference is now that the boundary of M is not empty. And we say that sigma 0 is rigid. And now if for any open subset U inside, so whose closure is in the interior of M, and this is open here, open, and then you can continue almost the same as here. There exists a neighborhood V in M. So this is a neighborhood of U. No, I still want global things. Gamma of it is a neighborhood of sigma 0 such that any sigma in there or any sigma in V, which is the solution, so that Q of sigma 0, there exists now an embedding of U, or a different embedding. There exists phi from U inside of M, which is an embedding, an open embedding, such that if you pull it back, if you pull sigma back, you have sigma 0. So such that sigma 0 is the pullback around phi of sigma. Right, so this is now an equality of sections over U. That's both of them of sections over U. Okay, so what happens is it's kind of similar, but uniformity. You fix your U first, or what you want to obtain this diffeomorphism, and then you have a corresponding V such that whenever you deform sigma 0 in this V, it won't be globally diffeomorphic to what you have, but only smaller. Okay. Here is a statement. And as a definition. I just want to give you first one example from symplectic geometry, which is basically just, you prove it just by using the Moser argument. So this is an example. So basically symplectic structures, but let's say some M, let's say it's just a closed ball of radius 1 around 0 in R N. And then we look at closed two forms, so E would be wedged through R M. Going to be wedged 3 star L Q your derivative. And then sigma 0 is the standard symplectic structure. So then let me also write it as a conclusion, then sigma 0 is standard symplectic structure. EXI YI or I is rigid.
But it is an only generalized condition on the sigma is under some presymplectic forms which are.
So this would be in this V, because this is an open neighborhood of sigma 0, which will contain only symplectic things. Right? Because it will be, I see. That will be the C0, but actually you need, and you have to think a little bit how the Moser trick works. So this is really the Moser trick. No Nash, just Moser. Here, and then if you think about how it works, you see how big this V is, and also that it really, here you really have to, you can't have rigidity in this sense, in the first sense, global. You really need to shrink a little bit, and then whenever you fix something smaller, you can. But then it has to do with the fact that you find this time-dependent vector field, but that might flow out, but it will, its flow will be well defined on this U, whose closure is an interior. If this V is small enough for sigma values. Is this clear to everyone? How this works? Yes.
Sorry, just to be sure, this means essentially that the rank of the form is already full, so it cannot kind of jump up nearby.
Yes, but that would be inside V, because V is a neighborhood. So in this one you can make smaller such that there is all this one exists, right? So that's one thing. Of course, also as Aldo suggested earlier, you could encode it in the E if you wanted. You could look at E to be not degenerate two forms and not, but in this case. Okay. Okay, now, so the point would be to obtain such a rigidity result, so to have a PDE with symmetries and say that under some conditions, such a result holds. And for that, I will rephrase this in terms, so a lot of this was, is basically due to Hamilton. There are these papers, these Nash-Moser, about the Nash-Moser inverse function theorem by Hamilton, and where he develops this part, but for him, he works with Frechelli groups and Frechet manifolds, we try to keep everything with PDEs such that it's very close to applications in the end. And then what he does not apply in these settings where you have boundaries, but it does apply in this setting. And now I will write what Hamilton calls the nonlinear complex associated to this problem. And then it's infinitesimal function. So to have this problem, you can look at the following things. Like you can look at so you can build something like a differential, like a chain complex, but it's a very short chain complex, which consists of the following. You have diffeomorphisms of M, and sections over M of E, and then sections over M of F. Here the map is Q, and here the map is just the action on sigma 0. So I call this P. So P of a diffeomorphism, P of phi is simply the phi acting on sigma 0. So phi star of sigma 0. And you can think about this as a chain complex. This is precisely our assumption that, well, it's one of our assumptions.
So sorry, sigma 0 is not fixed.
Yes, sigma 0 is fixed. So this is a chain or a nonlinear chain complex associated to this sigma 0, which we want to show that it is rigid. Right? So then we have the Q composed with P. This is just 0. Right? Because we know that the diffeomorphisms sends solutions to solution, sigma 0 is the solution. We're done here. So this one holds. Right? And basically what we want to show is really that this complex is exact in the sense that whatever I set here to 0 comes from here. Whatever is any sigma which is mapped by Q to 0 is actually in the image of P, but not globally, only around sigma 0. So it's somehow locally exact. And right. So the question would be: is this locally exact around sigma 0? And then you can kind of, first what you can do, you can look at finite dimensional version of this problem. So, I just put here now in finite dimensions, what happens is that you can look at, let's say that you have manifolds X, Y, and Z and maps like this, and P and Q, which satisfy these properties that Q composed with P is constant times 0. And let's fix here a P0 and here an X0 and here a Y0 and here a Z0, which are related by this map. So this is P of X0 and this is Y0. Right, so look at such a chain, like a nonlinear chain complex like this, and then you can linearize it simply by taking the derivatives of these maps. Right? So if you take the differentials, then you actually obtain a linear chain complex, right? Px0 of x. You can, and I'll denote it simply by P1. So this is the differential at x0 of P going to Dy0 1, and then D2, which is simply the differential at Y0 of Q going to Z0 X. Right? So I denote them suggestively D1 and D2 like two differentials. And if by the chain rule, we simply have the D2 composed with D1 equals 0. And in this finite dimensional setting, you can prove using usual implicit function theorem that if the linear chain complex is exact, then also this chain complex is exact. Okay, so
around y0.
around y0, exactly. So or around, yeah, around y0, yes. So basically by the implicit function theorem, you can prove that if the image of D1 equals the kernel of D2, so if this is exact at y0, then, and let me just write it like this, then the image of P, so P of x is a neighborhood of y0 Q inverse of Z. Right, so this means it's exact. It's open. So everything which is sent by Q. You can even prove more that you can find a smooth splitting somehow which satisfies certain point. It is splitting in some sense. I'm not going to talk about this. But this is something like it's a differential geometry exercise. Maybe it's not very easy, but it uses the implicit function theorem, and it's not hard to check. And now the point would be to do the same thing also for this complex, for a nonlinear complex, or for this one that is still written here, and to linearize it and to see if one has such a theorem, like if the infinitesimal conditions imply the global condition. So first of all, also here you can talk about differentials, but I'm not going to make it into an infinite dimensional manifold, but just write them down. So in our case, for our nonlinear complex, what would be the linear complex? Well, it's simply differentiating those two maps. I will not write much more than that. So the linear complex would be, so the linear complex would go from, so the role of the tangent space at a group of the group of diffeomorphisms at identity are multi-vector fields. Then this is actually the only reason why I'm working on with vector bundles is to not to replace this by anything and write again sections. And then here we have sections of and this D1 and D2 are simply the differentials of those two maps. So D1 of vector field V, you take P over the epsilon equals 0 of P of the flow, right? For example, use the flow here. So the flow of V times epsilon, and you can put back sigma 0. And this will be a path of an actual smooth path of section. So if you take the derivative, you'll get a section, and similarly also for D2. So D2 of let's say of eta will be over the epsilon when epsilon equals 0 of Q of sigma 0 plus epsilon eta. Right, so these are the operators. Now both of them are linear. So both D1 and D2. 1 and D2 are linear partial differential operators. D1, you can think about what degree they are of. D1 has to do just with the degree of this natural bundle. Natural bundles have degrees depending on certain jets. And so to prove this one uses this theory of natural bundles. And for D2, this follows basically from the definition. If you differentiate this will be linear partial differential, right? So this is our linear complex. And we would like to say, well, if the cohomology is trivial, then it is locally, the nonlinear complex is locally exact around sigma 0. And such a thing holds, we can apply this theorem of Hamilton to prove such a thing in the case where the boundary is trivial. But then the fact that the cohomology is 0 has to be encoded in a more, what should I say, quantitative way. It's not just that the cohomology is 0, but one needs to be able to produce primitives somehow which are bounded. I will write this in a second. So, well, so first I'll start with from the theorem. Basically, it follows from this implicit function theorem of Nash and Moser by Richard Hamilton. And moreover, not just this follows. I mean, he basically appeared also this setting somehow in his papers for example, for foliations. Applied it to prove the results on rigidity of foliations. And then, so the setting will be exactly this one that we have. Q is so Q of, let's say, sigma equals 0 is natural partial differential equation, and we take and M, the boundary of M is M. Right, and we take sigma 0 is a solution, and then we want to say that, well, if the cohomology vanishes, then we have a linearization result. Now, but even for the complex calculating this cohomology, you get vector field sections over M and sections over M. And the cohomology being 0 is equivalent to the existence of linear homotopy operators. So this is something also Florian mentioned in this talk, these homotopy operators. And then something, this is just linear algebra. The fact that such a chain complex has trivial cohomology is equivalent to the existence of linear maps H1 and H2, such that which satisfy the following homotopy relation. So the identity on sections of E, we can write it as, so we do H1,
the theorem is saying that H1 and H2 exist, or it's
an assumption. Sorry,
it's an assumption.
Assumption. So assume that, maybe I should assume that there exist linear maps. And there will be here, so two maps like this. So they are homotopy operators. I'm just I wanted somehow to say that this is natural in a way that if you want the existence of such linear operators is really equivalent to the convergent zero. This is why I phrase it in this way. But now we are going to assume about them that they are bounded also. And this is what this inequalities that Florian's wrote. So such that this holds, and the norm of hi of, let's say, of eta k can be bounded by, and in this classical setting of the implicit function theorem, it will be the norm of eta and a fixed shift in the group. And this constant with anarchy.
So that's lower I, right? Hi.
Yes. So for both of them satisfy this inequalities. Right, so it means that, so this is for all k. Okay. This holds, and d is fixed. Let's say d is fixed. So if we assume that this holds, then rigidity holds in the sense that I defined earlier. Then sigma 0 is rigid. So, are there any questions about this statement? So somehow the magic here is, and it really depends a lot on the problem, how you build this H1 and H2. It really depends on what geometric problem you're looking at. For foliations, in what Hamilton used this to show rigidity of foliations, he developed some pseudo-differential calculus adapted to foliations to construct this H1 and H2, and he proved it for foliations which have compact leaves and with vanishing first rank cohomology.
So what does it show?
That foliations which have compact leaves and I think vanishing first rank cohomology, all of the leaves have this property, satisfy this, are rigid. So any nearby foliation will be equivalent to the original.
And how are foliations, what is the Q for a foliation?
So, I mean, here E will be the Grassmannian, and Q will be the integrability condition for a section of the Grassmannian. The section of the Grassmannian will be a distribution, and Q will be the involutivity, and that you can write as a two-form. It's actually a bit more complicated because naturally this bundle will be a bundle over this in his case. So the setting is even more complicated. Right. And then you also apply the complex structures to study properties of complex structures. Okay. So I have 10 more minutes. Okay, so now I will talk a little bit about our result with Roy. And I will just modify the statement because it will be.
We can adapt it to singular foliations.
Hope so. But I think they are a bit more difficult to describe as a geometric structure. Yeah. Yes. What do I want to do now? Like just modify this. So the first modification will be this one. So and so this is what we proved with Roy. So the boundary is non-empty, and now what we do is we kind of fix a color neighborhood of the boundary. Okay, I think maybe I'll erase it. Sorry. So, just to state it is. For PDE, and then the boundary might be non-trivial, but then we fix an identification of M around the boundary, so around the boundary with, so a color neighborhood with 0, 1, so that 1 is the end of M. This is M, this is 1, this is 0, and we'll call MR whatever sits to the left of R. So we define MR to be what corresponds under this isomorphism to M minus boundary of M times R1. Okay, so this is MR. And now we are assuming that we have some homotopy operators which do the following. So assume that there exists linear maps. And so here we have vector fields on MR. One was going to vector to, let's say, sections over MR. Two was going to sections over MR. And well, we could just assume that they go backwards, but somehow in applications, what appears many times is that it's easier to build these homotopy operators when you give up a bit on how on the domain of the element. So we actually assume that they go like this. So for each S smaller than R between 1 and 0, we assume that there are maps like this H1, which should have also an R and an S index here, and then H2, R and then S. The sections of N, S, F. Such that now the homotopy relation is similar, so H1 composed with D1 plus D2 composed with H2 is the restriction, because here you can restrict. Okay, so such that just like H1 composed with so D1 composed with H1 plus H2 composed with D2 of an eta is eta restricted to the scalar form. And so this is the homotopy equation, and then they satisfy the same type of inequalities. So, and sorry for the order on the blackboard, I'm writing inequalities here, and they satisfy the same type of inequalities. Norm of H RS by eta, norm of eta K plus E.
Then it's rigid. Then it's rigid.
Yes. Then sigma 0, which didn't appear yet in the statement. So yeah, so we also fix the solution. Q of sigma 0 equals 0. So then sigma 0 is rigid. Okay, but the complex is associated to sigma 0. Right, so this should be clear. Sense otherwise. Right. And here, so somehow in applications, sometimes it's just easier to build them if you shrink the radius than if you keep it in some other application. So, for example, one application is the Const theorem, that Florian mentioned for linearizing Poisson structure. This would be one. This is one application of this result. But not the result that Florian talked about. That doesn't fit here. We thought when we wrote this that everything will fit in here, but because we somehow thought that whenever you can build this AGIs in an example, they will satisfy such equations, but no, like in how we build this with Florian, they do not satisfy. We don't know one can prove that it satisfies such inequalities. And then we started working with these two double index forms. But it's another story. So just finishing with this one. And for more minutes, let me just say something about the Nijmegen theorem, which fits in this.
Technically, you don't have 5 more minutes.
No, I said 4.
The old 4.
Okay, now 1 minute passed already. I don't have any more time.
I mean, you can go a couple of minutes.
I remember 14. That's what I remember. You said 13.
410. Exactly.
Oh, so I have 50 more. I think there's not much more what I want to say. It's just so for this new London, I think what I want to show is how rigidity implies normal form theorems. That's a bit what I want to show in the end. Right, so what does it say? So you basically have this J, which is, let's say it's something local. So on the ball of radius 1 around 0, that's our endomorphisms of Cn. So this is the ball inside Cn. And which is an integrable almost complex structure, right? So J is equal to minus and Nj equals 0. And you would like to find coordinates to put it, to make it the standard complex structure on Cn, right? So this would be the new random theorem. And then the trick would be the following. So you want to, let's write it like this and find phi such that phi star of J is J0, which is the standard complex structure. Right, so these are n-terms and blocks. And so how could you do this? Well, assume that J0, J at 0, I mean J at 0 you can change just by a linear map, and you can assume that this is J0. And then you can pull it back by multiplication by t, this J. And you'll obtain a smooth path, Jp, which also empty star of J0. So this is a smooth path of things because you pull back by multiplication by t, they're all diffeomorphic to J. They're all diffeomorphic to J. But then the limit at 0 exists, and it's exactly the constant one, J0. So you can connect it by a path. And if you know that J0 is, so if J0 is rigid, it will follow that Jp is isomorphic to J0 around 0 for some t. Some collective t. And then you're done, right? Because all these Jp are the multiplication by t isomorphic to J. What I want, maybe you don't really understand right now, maybe this one very fast, but somehow the idea would be the same for all structures. Somehow. This is how rigidity implies linearization. You find like a path, and paths are usually given by multiplication, by rescaling and stuff like that to the standard structure. And now you only have to build for this one the homotopy operators. So the homotopy operators are part for the J0. And in this case, it will be, so you basically decide the homotopy operators for the Barkov homology, H1, the bar of the standard complex structure. And those are some standard things which appear also in the proof of the theorem. But you end up with some standard things. And I'll stop here.
Okay. Thank you for your talk. Other questions?
Does this strategy avoid the difficulty of the proof of Ioan der Nuremberg, or is it just encapsulating it in an easily generalizable way?
The second, yeah. And I think maybe this proof will be in the end more difficult than the many existing of the Ioan der Nuremberg. But it's one statement that you can apply in many situations. And also the bounds, I don't think they will be very efficient. Like if you think about, I don't know, if you want a CK diffeomorphism, if you worry about not just the degree of differentiability of this diffeomorphism and so on, it will not be optimal at all.
So they are not C-infinity?
They are C-infinity if you work in the C-infinity category, but people also prove that if you have a C3 complex structure, then you find, I don't know exactly what the degree is. So this also exists, and that's kind of used because I think the first proofs of the Nuremberg were in certain supported basis. I think.
Other question online? Oh, well, there is still in the audience.
So as far as I recall, in the Nash-Moser theorem, you have to invert the linearization, not just at the solution, but in the neighborhood. And apparently in your formulation, the assumption is only at this very point. So my question is, how much work is involved in your proof to finally be able to apply the Nash-Moser theorem?
So first of all, in the setting of Hamilton, and the theorem that I wrote, that I said it follows from Hamilton, so it comes from, right, so Hamilton's result would assume that the sequence is exact not just at x0, but at points around. But now we're working with a Lie group, with a Francesco group, and I was assuming that everything is equivariant. So somehow if you have exactness at one point, you can conjugate with the Lie group action and obtain exactness around. And this is also in Hamilton's paper. He realized this and he writes this. Now, in our case, we don't apply a theorem, we just prove things kind of by hand that this holds. And this is more inspired, I would say, by the proof of Kohn from Poisson geometry, of Jack Kohn for this linearization theorem. So but we use the action all the time, somehow. And the homotopy operator is only at one point. So somehow it's an iteration which at every step kind of hits this sigma with a diffeomorphism, which brings it a bit closer to sigma 0. And then the infinite composition of all those diffeomorphisms would be the final diffeomorphism. This is how it works.
Sorry. Yeah. I'm not sure I understood your remark about using the group action, because the orbit of the group, so in this intermediate, in the complex where you wrote, the nonlinear complex, the middle space is where you have the open neighborhoods, right?
No.
And where you have to prove the invertibility pointwise.
No. Not in this version of Hamilton's inverse function. So in the version with the sequence, you need to prove invertibility on an open set in the first space, not in the second. So he has this x, y, z, a sequence of two maps, and now you're in this setting of tame Francesco spaces, such that Q composed with P is a constant Z0, and you fix this x0. In the first one, you have to show in a neighborhood of the x0, not of the y. This is how Hamilton's theorem works.
This is in Hamilton's original paper.
Oh, yes. And I think here he puts like two maps. He has even a more general setting than this one. And then he has also an unpublished paper where this think about foliations, there's the proof of plot foliations. And there he does this again.
Okay, thank you. Maybe I'd like to have a look at that unpublished paper.
I have it.
Okay, all right, thanks. Did we get anything online?
No, nothing here.
Okay, then if I don't see any more hands, I think we can stop and thank again, Jonas.